This video is going to show you how to find the electric field at a point in space due to another charged particle. Let's start with this. I've got a negative particle in space, and the first thing I want to do is I want to figure out the direction of the electric field just in space around it. So to do that, I have this imaginary test particle, and I think to myself, what would happen if I take this imaginary positive test particle and put it near the negative particle? Well, it's going to race towards the negative particle, and if I have a bunch of them, they're all going to make a straight line towards it, so it's going to look kind of like this, kind of like a ray of sunshine around a little negative charge. So that's going to be the E field. But what I want to do is I want to find out what the strength is of the E field in this point of space along these E field lines. So to start with, I'll have my imaginary test particle, call it Q1, and it's going to feel a force equal to Q1 times the electric field in this point in space. But since I'm talking about particles, my force that it feels, that can come from Coulomb's law. So F is equal to K Q1 Q2 over R squared, where Q1 is my imaginary test particle and Q2 is the actual particle that's sitting there in space. Now, because I have two forces that are both acting on the particle, they're really the same force, so I'll set them equal to each other. K Q1 Q2 over R squared is equal to Q1 times the strength of the electric field. And that's great because I want to find the electric field strength. So I'm going to solve this for E, the electric field, and that gives me K Q2 over R squared. Remember that Q2 is equal to the original particle that's actually sitting in space, not the imaginary test particle. So I'm going to write this as E is equal to KQ over R squared. So that's how I can find the electric field's strength at a point in space. This will give me the magnitude of that charge. And when I'm using this formula, I don't put in a plus or minus charge, I just put in the magnitude of the charge to figure out the magnitude of the electric field. So now let's go on to another example in 2 dimensions. I've got two particles. I've got the B particle and the C particle, and I've got this pulsating point in space where I want to figure out what the electric field is going to do. Because remember, the electric field provides the force to any particle I put out there. So to find my direction of the electric field, I'm going to use my definition for the electric field. Remember, the electric field points in the direction a positive particle would travel. That was my imaginary test particle that I recently did. So here are my two particles. C is positive and B is negative. I'm going to take an imaginary positive particle and I'm going to put it right there at that spot in space and figure out which way it would go. So here's the particle, and C, because it's the same charge, is going to take that particle and push it away. So that's going to be the direction of the E field. So that's the direction of the E field due to particle C. Now let's find the direction of the E field due to particle B. So I'll take my imaginary positive test charge, put it in place, and let it move. So I imagine it's going to be attracted to B since B is negative. So my E field this time is going to go from left to right. So now I have the components of my E field. If I had more vectors, I would draw more E fields, and then I would sum up the E fields in the X and Y direction. But this time I only have 2, so that's pretty straightforward. Now I'm going to find the magnitude of each of these E fields. So to find the magnitude, I'll use my formula. E is equal to KQ over R squared. And I'll first find the magnitude for C. So the 8.99 times 10 to the 9 Newton meter squared over Coulomb squared times C's charge divided by the distance between C and the point in space. That gives me the 383.1850 newtons per Coulomb. And I'll do the same thing for the B charge, and this time for Q I'll put B's Q in there, in other words B's charge. And I get the value of 100.58 newtons per Coulomb. So now I know actually how long those two vectors are up there, those two little components of the E field. So the next step is to draw my final E field triangle. So I'll take the horizontal component, and then I'll use the vertical component. And those are the pieces of the E field. I'll follow this by completing my triangle by drawing the net E field from the very beginning of my vector combination to the very end. That's the net E field, and it's going to have an angle. Now I need to find out magnitude and direction of the E field. So to find out the magnitude, I'm going to use Pythagorean's theorem using my E fields. When I use Pythagorean's theorem, I get my net E field to be 396.1658 newtons per Coulomb. And to find the angle, well, I've got the opposite and the adjacent to the angle. So to find the actual angle, I'll use the tangent function. Tangent theta is equal to 383 divided by 100. And when I do that, I get 75.3 degrees. So the net electric field at that point in space, due to the B and C charge, is 396 newtons per Coulomb at an angle of 75.3 degrees. Now, let's make this kind of show you how this compares to Coulomb's law, some of the previous problems that were done. Some of the previous problems that were done, I can look at the process, and I can see that the process is actually very similar. So here's my little Venn diagram. I'm going to start with the net E field and the net electrostatic force. In other words, Coulomb's law and the E field. And I can see where they're going to overlap So in the beginning it's a little different. I'm dealing with forces and dealing with fields. But once I've identified the forces and the fields, it's all the same process. I'm combining by summing up the forces, I'm combining by summing up the fields, I'm getting a net field and a net force in the x and y directions, and then I make my triangle, find the hypotenuse and the angle. So it makes it pretty much the same process.